For next presentation, I'm happy to introduce Professor Tom Molkens from KU Leuven in Belgium. Tom, the floor is yours.
Thank you, Thomas. So title page, okay. Outline. This is a case study, and I called it in the previous slide retrofitting, numerical retrofitting. It's something which happens at the moment that you are coming too late, in fact. So it's not really fire safety design, it's fire safety retrofitting, something like that. It could be a nice discipline because I'm mostly involved in such kind of operations. So we will do a small tour, building description, a problem statement, and we're going to do a simulations with SAFIR based on a 60-minute ISO 834 fire, the standard fire, which was required, but we didn't achieve it due to some execution errors, and then we will clarify the methodology that we followed and give you the simulation results from natural fires and the solution that we obtained. So building description it's a nice building. This is a sport building. It doesn't look like that, but nevertheless, at the moment that you have a look at the inner side, you see that there is a sports hall. It's a very nice one. There is also a fitness room included, and there was the school building on top of it. So the upper floor with the glazing that you see, that's a school building. It doesn't look like a school building, but nevertheless, there are classes in it. But what you see on the left top figure is that there is a nice truss beam included. So there are nice truss beams in it. And then lastly, there's also a taekwondo and gym hall included in the building. All nice, and this gives some sections, and what we see in the sections is that you have at the top figure, you see that you have the sport hall here situated, and then the sport hall, on top of that there are some classes situated. There is an outer space there, and then in the second section that you see the taekwondo room there, and that you see also some nice room for people, fitness rooms, and such on. And then you see already a light on the structure. It's in gray. You see there's a truss beam included, and this truss beam is positioned on top of a central stiff core, making a cantilever to the left-hand part, and then you see that the other part is supported by a concrete wall. Now, so the truss beam, but the truss beam, it's not really a truss beam. To make it everything more complicated, there is also some Vierendeel action in it because you have some passaways through the truss beam. So there are some Vierendeel action in it. So we will drive at a very high and heavy profiles. There is a cantilever part, the central core, like I explained a few minutes ago. What do we see in the other direction? In the other direction, horizontal, so you have the sport hall, the taekwondo guys, and level higher than you see in light blue. It's an opening effect because it's a double height, the sport hall. You have the fitness rooms there, you have some sanitaries and such on in the central part. And then at the top part of the building, you have classes which are going around. You have direction, archive, some flex rooms, and then the blue one is an open space. So you have in the central part of the top floor, there is an open space, which is an open corridor where people can go out and that can just run around. And then in the rooftop part, you will see that there are two truss beams. You see this part, you see already that the truss beams where they are situated, they are in a regular grid. So there's the one, the second one, the third, the fourth, the fifth, sixth, and then the third and the fourth. Those truss beams, they are just passing through the whole building, going from inside to outside. And on top of that, there is a steel frame, and on that steel frame, there's a cover and some photovoltaic panels. So in basics, those two truss beams are connected to each other. There's a stabilizing effect, but I didn't take it into account in the simulations. Okay, so this is the truss beam. You will not see on your screen, but I will try to make a magnification of it, something. Perhaps then it becomes clear. There are some numbers for the vertical studs, and they called it V10, V15, V20, and such on. And the V, it means that's a vertical stud, and that's nice because in English and Dutch it's the same. And then the 10 is the millimeters, so the thickness of the hollow section. So you have 10 millimeters at the right-hand side. Then we have this Vierendeel action, then it's a 15 and 20 millimeters, and then you see that it's going 10, 10, and so further. But there is something which is not that logic, and it comes out at the moment that you're working in a fire safety design. Mostly at the moment I do fire safety assessment, then I start first to check if the right profiles are used, and there is something strange which is happening here. Because the support is at the right-hand side and they're at the left-hand side. And what you should assume is that the most of the weight is on this vertical one, this one, because this is an incline, it's pulling all the forces to the top and then pushing down. And this has only a section, cross-section, the thickness is only 10 millimeters, while the next one is 15 and that one is 20. We have 10, 10. It's going up to 15, okay, nice. The diagonal is also 15, and then again it becomes 10. The compression stud is 25, and there is 10. So there is something going on. Also here, I see that my rectangle is not going far enough, but you see that the most loaded vertical studs, they have the basic thickness, and it seems not to be logic at all. Again, this is the same, and now you see the cross sections, how they are composed. So you see that the upper part that is a horizontal beam with the two lips on the side. Then you see that the studs, the vertical ones and the diagonals, by the way, also there are whole sections which are composed out of plate of 10 millimeters, 50 millimeters, 20, 25. And then the horizontal bar or element, it's a shape that you see again, that's with two lips, and that we have this problem. There is also a good thing, and the good thing is that the top part of the beam is covered in some way or protected by hollow cores, which are posed on the left and right hand side, and which is the same equal thing for the lower part. So there we have some beneficial actions. So this is all steel, but the problem statement comes on. And what's the problem? Well, the steel contractor, they proposed a critical steel temperature of 650 degrees Celsius. And nobody knows where it was based on, except if you just take economical reasons. And then the problem is going further on. First of all, the architect, he was not aware about the standard of Eurocode 312, because there you could read that is 500 or 540 would be normal. The general contractor has the same concerns. He was not aware. The client, the consultancy office, they were absent of the meetings, and then the third party control, they say, the fire resistance is out of scope. And this was really a problem. So, and the problem was only detected by the fire brigade just before opening of the building. So completely finished. So then you have a really huge issue, because making a fire protection properly, then you should scratch off all the fire painting, doing it again. But you have all the finishings, ceilings, walls, everything was on the cladding. So it was almost impossible to handle this in a proper way. So there was no conformity with R60, excuse me for the Dutch text, but that was just from fire brigade. So they said, okay, it should be R60, but there was in fact only R15. There is also not a compatibility, because it's not stated of the internal painting with the external environment. And so the commissioning of the building was rejected. And this is a huge problem for a contractor, of course, because he doesn't get the last part of the money, and which is an important part. But the fire brigade was so nice to say, okay, you can ask for a derogation commission, but it will not be delivered by us. It's the Federal Ministry of Internal Affairs, and you will need some compensatory measures. Okay, the problem stating, and now the numerical retrofitting is coming on, and so we need some magic to get it done. Okay, let's see what we can do here. So first of all, problem statement, just checking what will happen. So we made a nice simulation. We did a partly simulation, so only the truss beam effect. And as stated before, it's like what we call now in the new upcoming Eurocode 0. So it's a direct method. So a direct method, it means at the moment that if you have a verification done with plastic models, then you can have a direct verification of the stability. You see that we have the top beam. We have taken into account the protection part of the concrete. We submitted the whole thing to an SAFIR lead for the 10, 15, 20, 25 millimeters, and also for the lower beam part. We did those simulations, and at the moment that you then run the simulations, we have to achieve normally 60 minutes of fire, but we know now there's without any fire protection, you will directly see, okay, here is the buckling phenomena, which was to be expected because there it was a very slender column, in fact, and it is the most heavy donut. No surprise at all. So, okay, at the moment that we do it with a 540 degrees Celsius fire protection, so it would be properly done, then we have a failure after 3,670 seconds. So in fact, it's one time step beyond the failure time of my fire protection. So then I asked myself also, is this a safe solution? This is not really robust, meaning that so at the moment there is one failure or one error made in the fire protection, the system directly fails after and before the time which was needed, the required 3,600 seconds, 60 minutes. So we are aware that there are some errors in the design. Errors, not really, but that's some strange things in the design. So we have to tackle this all, and how can we solve this? So we already know that the methodology is the red arrow that we follow, that we have the project design, the prescriptive rules, which are also in the contract, by the way, and repeated. That is normally R60, the member analysis, and then we can come to simple calculation models coming out of the Eurocode 312. That's a normal way that we can do. But there is also another way that we can handle, and that's saying, okay, let's go to performance-based design. Let's do an advanced fire development models, and then we go to parts of the structures, which we have been doing, and then we can go further on to an advanced calculation model. But we included in this check or verification a severity check, in the meaning that we said, okay, at the moment that we have our fire development, and we're going to do this for separate rooms and locations, at the moment that there's a natural fire is going beyond the eyes of fire, let's go then for a project again to the left-hand part of the figure. Let's dismantle the finishing. Let's agree that we have to do it in that way, that we cannot achieve a better way than just dismantle everything which is needed, and that we do a proper fire protection. In the other cases, at the moment that we are at the exterior side, because there are two truss beams which are partly exterior, then we can apply locally the external fire curve, and then at the internal part, let's go on with the natural fire and then just use the advanced calculation models. So that's more or less what we followed and methodology that we proposed. So the first step is fire developments in rooms. So we checked each room. So we did fire simulations with ozone for each room, and you see the numbers 2, 1, 2, 2, and so each room we did a localized fire, in the meaning that at the moment there is a compartment fire, it will start ignite in a room. So let's start with first the room, and then at the moment it extends, then we go further on. So we firstly said, okay, let's do some simulations. You see the number of simulations. You see also the ISO fire, and then we see, for example, that the room 215, which was a management room, and also the archive, that they are really severe fires, that they're passing or approaching the eyes of fire. So those two rooms need special attention, and the other rooms, therefore, we're going to use the ISO approach. And then the other two rooms are the room 212 and 211, which are very close to each other. And you see, by the way, that all those rooms are very close to each other. So the fire load seems to be more or less uniform. So, and then in the second, so we're going to use the room 212, so the Flex 2 room as a design fire, by the way, it's located there. And we're going to apply this design fire in the second step. But first of all, we checked, of course, also the sensitivity of the windows openings. And you see that, for example, with the double glazing or triple glazing, some rooms have triple glazing, other rooms have double glazing. So we checked both of them, and the triple glazing seems to be the most severe one, the highest temperatures. The double glazing gives a little bit lesser in temperature, but extended fire times. But for steel, it's mostly the peak temperature, which is the decisive one. So we took the triple glazing scenario. And then we go to step 2. So we have seen that there are some 2 fire compartments. So we applied those 2 fire compartments. We applied separately, or in the green or in the brown. And then the Flex 2 room fire load, fire load in the meaning of temperature time curve. So, and those two rooms are the exceptions because there we needed some fire protection. So the CEO has to leave his office, and we refurbished the whole office and also the archive. So at the moment that we are doing those simulations, then we see time scales, the temperature scales are a little bit different. But then we see, for example, after 30 minutes, why 30 minutes? I will go back because 30 minutes, that was even for both of them. You see here for the Flex 2, here at 30 minutes, 1800 seconds, then we have the maximum. And after 1 hour or 3600 seconds, we have not anymore the maximum. So I made just a copy of the 30 minutes, and the 60 minutes will follow directly. And then you see that the temperatures obtained are 555, 680. So this will be a problem. And the V10 is one, just exactly that one which was buckling. So this is the problematic one. The 25, that will pass because we know that at 520, something like that, it's fine. Also here, the major part of the profile seems to be okay. So there are some opportunities. So okay, and then what we have to do and what we thought, okay, let's insert also concrete. Instead of dismantling everything, let's drill a small hole in the tubes and let's insert concrete. So we pump a grout into it and we use the grout only as a thermal part, not as a structural element. And we use it only thermally. So in the mechanical part, this is an insulation, the insulation part, and then we can start to calculate what the temperatures are. And you'll see that we are only in the tips, we are getting over the 540 degrees Celsius. So it seems that it could be a solution there. And as we have also a problem, not for this truss beam because it's completely inside, but the truss beam which is going outside, we had also there a problem, and there we will go, because then we don't have this beneficial effect of the hollow cores at the left and the right hand side. We will fill it also there with concrete. And at the moment that you see, we did in total 73 thermal simulations, 64 mechanical simulations, just by adapting, because we have, they have been so nice to have 5 different truss beams. Not even one truss beam is the same as the other one. So each one is different, different configurations. So we did a lot of mechanical simulations, just changing and checking. And you will believe me that numerically doing this work is much easier than going on the spot and drilling a hole and just grouting everything full of grout. So that's what we did. And then after 60 minutes, we achieved this one, and then it's cooler. So that's because we are already in the cooling down phase. And this was finally the solution that we proposed. So we need some grouting works, and it will be not an exception. So for example, for our truss beam 3, the both ends, the most loaded vertical parts, studs, which it's pure logic. And I think even if you do the check according to Eurocode 3, and that you will need it also. There's some structural parts, but okay. It was out of the scope for me, in fact. Then at the moment that we did the same thing for the truss beam 4. So here we had the advantage. This diagonal was working in compression, but it was 25 millimeters in thickness, and this was only 20 millimeters. So this was more stiff and reacting more stiff than this one. Therefore, there was some distribution of moments, and therefore also here the second stud must be grouted. And then we have the truss beams 5 and 6, which are going outside. That's the reason why there is a light blue shaded area here. There's an area which is outside. Therefore, we injected with pure in foam some blocks, and then we injected also completely the grout here. Also for the upper part, which is outside, you see that we have 1, 2, and 3 vertical ones, and then for the 7 it's like number 3, and they survive the fire. Problem here is 3, 4, 7 survives the fire, and only 5 and 6 they fail, and they fail after 3,758 seconds. So it's already further than 1 or 2 time steps than the 3,600 seconds. But we made a remark that we didn't took into account the structural beneficial effect of the grout filling of the tube. We didn't take into account the stabilizing effect that both truss beams are supported by each other, because there was a steel frame on top of it with the photovoltaic panels. So that was an additional argumentation. Now, we did so, for example, and I don't know if it will start. Is it starting? No, it doesn't start. This is a pity. Okay, but you have to believe me, this is beam number 4, and that just pass. How could I get it done? No, I don't get it activated. Okay, but this is the moving normally, and you will see that it will pass. Now it's starting. Just pushing enter. So what we see is that the load was set on 20 seconds. You will see the previous failure time of 870 seconds or something. We easily passing this one. So the major influence of temperature is at 1,800 seconds. 1,800 we are approaching, and you will see that we are coming close with the deformations, so the displacements. But now again, we are coming in the cooling down phase, and you see that it's coming up back. So that's it passed completely the natural fire, so that is okay. Then we have the other one, but I should speed up, but I cannot see the thing. But you will see that also this one, after 3,700 seconds, it will fail. But you have to believe me, and the problem is the buckling again here, and also something with the rebar tension there. So there are some problems there. But in sake of time, I will skip the complete animation. Nevertheless, you see already important information of the cantilever part. So timeline, also interesting to do some timeline. The submission at the end of November 2022. Finally, we get an approval of the Ministry of Internal Affairs in June 2023. So an execution of the retrofitting works, they took place in 2023 in summer during the closure of the school. So what they said was that, okay, I will translate it as, so I admit you an exception based on the point 3.2 from Annex 2 of the Belgian regulations. And this Belgian regulations is about the fire time, which was requested. And this is the end of the talk.